I'm going to explain what we are doing at the Themis telescope now. For this talk, robust wavefront sensing will mean extract the slopes and the covariance of the slopes in real time. So each measurement comes with its error. I will explain first why and a little of the context, and how. I give some recipes, or the recipes we are working on and we are developing. And I will say something about how to use these covariances in the control algorithm and conclude. So the context is the Themis telescope. So it's a solar telescope, 90 centimeter telescope at Tenerife. You have here a picture of the wavefront sensor on the telescope. It's a Shack compound wavefront sensor. You have the geometry here. So it's 11 by 11 actuators, alpha ODM, running at 1 kilohertz. So we have very little constraints. I mean, the specification we have are not really accurately defined. So the constraints are we have to do it low cost. When I say low cost, I don't take into account my salary, of course. And the adaptive optics system must run unsupervised. So we are working here because we have the opportunity with this telescope to implement new methods and for reconstruction and control. Methods we are working for a long time on and working on simulation. And here we have the opportunity to bring them on sky. So the RTC we are developing is a standard PC with a suitable software for our methods. And to do, our mission is to do the best we can do. So here's an example of the signals we have. This is already a preprocessed images because without preprocessing we can do hardly, you can see hardly something. So why it's harsh conditions? Because it's adaptive optics in the visible. It's daytime with a medium R0, which is something like 4.6 centimeter. The sensing is on solar gradation. You can see in each subaperture 10 arc-second field of view on the granulation on 30 pixels. Yeah. And here you have 100 frames, and we repeat the 100 frame here. You can see that you have a structure, and so we can expect that we have not isotropic errors in the gradient, the coordinated gradients. It's a similar things as laser guide star elongation. And we have the structure changes, the coordinations evolve at the minute scale, so it's similar as sodium profile evolution. The condition may be more difficult sometimes, so, and as the system must run unsupervised, we need to adapt to this sort of conditions. So a key point is to get the controller after inform on these situations. So we want to have to inform on real time on the errors. What we see also is that at a given time, the sub-images are more or less blurred. So when we make a reconstruction, we have to know where are the good gradient and the bad gradient in the same wavefront. And from frame to frame, it's evolved, of course. So here we focus on robustness in this project. So it means that we want to promptly adapt to varying conditions. Unsupervised and the best in any conditions means auto-calibration. So I will not discuss this point here, but it's a main part of our work. we have an evolving system because the interaction matrix is evolving because we have a ceiling pointing mirror inside the beam, and it shifts the image of the DM. And we have a derotator somewhere in upstream, so decentering of the pupil. The recipe is that we want to estimate the errors and the covariance of the slopes to optimize the system. And so it means that before we want to work out the errors on the pixel values. And then we have to take account of this in the comments. So, so I start with working out the errors on the pixels. Here is this slide is quite standard, so it's just to explain how we model the things. So we have the raw pixels, which are proportional to the flux and the transmission from sky to the pixels, and including the quantum efficiency, and the gain, which convert the electrons in digital level, bias and noise. So it's classical. And so we need 3 frames for calibration. Actually, it's a set of frames, so it's a bunch of frames. And because on some of them we want to have the variance, not only the expectation or the mean. So we have dark, flat as usual. So flat means that all the pixels receive the same amount of flux on average. But we had also what we call a static frame. It means that we don't know the flux received by each pixel, but we want it to be fixed and stable during all the acquisition of the set of frames. So concerning the value of the pixels is a standard way. So we have a linear composition of the raw pixel to get the calibrated value. It's just minus dark divided by flat minus dark. But if we want the variance of this value from the model here, we end up with this relation, which is also linear. Using these coefficients here for each pixel, computed this way. So we have to compute the gain of the detector and this value where we have the variance of the dark and the variance of the static frames, so-called static frames. So it means that at the end, compared to the classical processing, we have double the amount of calculation, because you have also to make something for each pixel, which is similar to a calibrated value to get the variance. So now when we have the variance, so now we call that the weight of the pixel. So each pixel comes from its weight. The weight is the inverse of the variance. So I call it W here. To get the error, the value of the slopes, we want to minimize a general cost function, where, of course, I've added some regularization. So we have plenty of things to measure, and also to disentangle the different parameters, we have to determine parameters that we don't want at the end, but it means it's the way to disentangle the contribution. So I explain how we model this. We have somewhere a reference image we don't know. It's the actual granulation we observe. This reference image is shifted by an amount we are looking for. This is written this way because this shift is nonlinear in respect to the shift we are looking for. We multiply by for each subaperture, K is a subaperture, we multiply by the constant because we have scintillation, so we have to take into account this, and we fit the pixels for each subaperture. But we also, as we can see, that the model we want to determine is an average, somehow average model, and we have seen that in the subapertures, the subimage has distorted. So when you fit something, the model is not correct. So to solve this problem and to take account more accurately to the correct error, including the error of the model, we rescale the weight of the pixel by a factor here we are looking for also. So for Christophe, when we start from the maximum likelihood and we have parameters in the weights, it means that you have a constant on the PSD that we cannot suppose that is fixed. So it's why it gives you this log term, which is log of this parameter of the scaling, and MK is the number of pixels, just a number of pixels. And the regularization here comes from to put constraints on the reference image, and mainly is for extrapolation, because we don't know, we have not all the data to know the reference where we want to know. We will see after. So we have to fit that. So the first step, as very similarly to the matched filter, is to linearize the system so that we can solve it. So this part here is linearized, and so this part saying that we have a small displacement compared to the expected position as the matched filter here. So this become a linear relationship, but differently with the matched filter, we have also this scaling. So we have 3 degrees of freedom here, which is written this way. The alpha here comes in now because it's linear. And so this cost function has a quadratic expression with these terms. Okay. And as a classical solution, so you have this expression of the solution here that gives you the displacement of the subimage here. And also what we need is to compute the value of the cost function at the optimum. To give you an idea, it's a matrix 3 by 3 for each subaperture, so it's almost no calculation. And here is a free multiplication, so it's very short amount of calculation. Okay, so now this now is known at the optimum, so we know the value. So we want to minimize this for each subaperture to find the factor, the rescaling of the errors. So it means that it's simple, optimum, you get this rescaling coefficient. So it's a step 2. Then step 3, we want the covariance matrix of the slopes. So as usual, usually it is just this matrix we have already computed. But since we have a change of variable between u and the x and y we are looking for, we have to use the Jacobian matrix for this change of variable. And this is the covariance matrix. So 3 by 3, because we have the covariance between the scaling and x also, and y, all the combination. And we only keep the coefficient between x and y, xx and yy. Okay? So at this time, we can send all this information to the controller. But now we need also to have this reference image, which is with the same cost function. We want to get this reference image. So how it is done is once you have determined everything before, so this you can write this cost function as a linear function is a shift of the reference image to fit the subapertures, the subimages, with a regularization. And we solve this using conjugate gradient because it's a very sparse systems. So, and we use this estimation to update the reference. So it gives you, so you have this kind of results. So it is the same frame as before. You have the cross that gives you the position of the subimage that locked on the subimage, and you have the ellipse, which gives you 1 sigma error. So you can see that at the edge you have a larger error. You can see also that the X is more accurate than Y because of the structure of the subimage. You can see also that we extrapolate this is the reference image, and we can extrapolate out of the field of view because thanks to the shift of the subimage, we know outside. And it's smooth because of the thanks to the regularization. Okay, and of course, in the worst case, we have the information that okay, the measurements are not good. Here, the elongation is more in a diagonal, but we know and we can optimize reconstruction. So now, how to use that in a controller? Usually, when you compute the command matrix, you start with a measurement, the model of the measurements. So you have actuators, interaction matrix, and which give you slopes with errors. And you want to minimize the viscous function. Here I put the weights, taking out on the errors. Generally, people don't use that, but so it's weighted least square here. And you end with this estimator where you need to pseudo-invert this matrix. Usually you use SVD or truncated SVD. But here, if you update at each frame the weight, or the covariance matrix or the slopes, it means that you have to invert the matrix at each frame, which is not really realistic. So we use an iterative method. So it's based on the conjugate gradient and, for instance, the fractal iterative method. So we have just to solve this iteratively, which is faster. And doing that, we can, on the fly, update the covariance matrix of the slopes. So the conclusion, I've shown you the path between from errors on pixel, covariance on the slopes, and iterative reconstructor. They should give you the input, the update of the commands. This is very similar to the laser star problem of the laser star elongation. We could use such an algorithm on that. You would have the actual covariance instead of the model one, so particularly when you have truncation. So you should have the actual error taking into account the truncation and the evolution of the sodium profile. Also, you have seen that we can extrapolate, so it means that we can know outside the truncation, we can know part of the profile. And also, on the night time, I took data from Canary, and you can see that, so it's a statistic on, because we have not the pixels, so it's statistics of the slopes, but you can see that it's quite inhomogeneous, the noise, and so better reconstruction should be achieved by taking this into account, of course. That's all. Thank you.